This assessment asks us which carbonyl, which carbon-oxygen double bond, will absorb light at a higher frequency, the one contained in an ester or the one in the thioester. For that, we need to draw our two resonance structures, or one resonance structure for each of these, and examine the effects of the different substituents. So there is the one for the ester. For the thioester, we'll do the same thing. And then we'll consider the different effects of the two groups. Now, if we look at the oxygen, we know that the oxygen is more electronegative than carbon, so it's going to be inductively withdrawing. So it's going to withdraw electron density by induction. But it can also donate by resonance. So we have inductive withdrawing and resonance donating. If we come over here to the sulfur, we know that sulfur is slightly more electronegative than carbon, but not to the same degree that oxygen is. So we might draw a slightly smaller inductive arrow, or maybe we'll write in smaller numbers that, or in smaller letters, that the sulfur is inductively withdrawing. Being less electronegative, it makes sense then that sulfur is also going to be a little bit better at resonance donating. Regardless of how good the sulfur is at resonance donating, its lack of induction is going to mean that the net effect from sulfur is going to be to stabilize this positive charge compared to the oxygen, where the effects are nearly equal. And so what we could say is that the carbon here is going to have a smaller or a more delocalized positive charge. And if it has a smaller or more delocalized positive charge, this positive charge here is going to hold this oxygen less tightly. Therefore, this one will absorb at a lower wave number. Alternatively, the one with the larger positive charge on that central carbon, or the less delocalized positive charge, it will hold this oxygen more tightly. The ester will absorb at the higher wave number.